We are talking about Riemann mapping theorem. Which says the following. Given proper, simply connected, set omega, there exists a conformal omega and any point z0 belonging to omega, there exists conformal f from omega into the unit disk such that f actually, the image of the thing is the unit disk. F of our chosen point is 0, and the derivative at that point is a real number, which is positive. Okay. And the power of this theorem is that we can turn any question we have about something on a simply connected set, no, say that better. We can turn many questions, many things we're trying to do on a simply connected set into something we're trying to do on a disk. Because this is a conformal mapping, we can go backwards and forwards with it. It just completely turns things into a nice calculatable set. And let us launch into the proof. So, step one was to do a reduction. So step one. We're going to reduce this problem down to having omega being a subset of the unit ball which contains 0, and we're going to have a map that maps omega into the subset of the unit ball. It'll be a conformal map which sends z0 to 0. So in other words, we can reduce everything down to something that's already inside the unit ball, and the role of this z0 will be replaced by 0 itself. Okay, so there exists, I'll draw a picture in a second. So I called this guy F, but I'm going to call other things F too, because I'm going to run out of this otherwise. So there, well, maybe let's not start that way. So there exists some G from omega into the complex, into the unit disk, such that G of Z0 is 0, G is conformal, and this time we don't mean that G of omega is equal to the unit disk, it's just contained within the unit disk. Okay, so we have some arbitrary simply connected set, might be unbounded, whatever, and we're going to find some mapping G that maps it into something which is simply connected but lives inside the unit disk. Okay, and 0 will be a point inside the image of this thing. So this is what G is going to do. It's going to reduce the problem down to something which is nicely contained inside the unit disk, and we're not having to worry about Z0, we will just have 0 itself. Okay. And once we do that, then we can consider the family of functions that map things from this subset into the unit disk, whose derivative at this point has certain nice properties, but we'll get to that in a second. So this first step is simply a reduction. So how does this go? Okay, so omega is a proper, simply connected set, so it doesn't contain the entire complex plane. So there exists some alpha belonging to the entire complex plane, take away omega itself, by definition of being proper. And the first step to getting our G is we're going to define G tilde, say, of Z to be the following thing, and I'll write it down and explain in a second. G of Z minus alpha. Okay, so why can we do this? Well, this set omega is a simply connected set, and we've taken some point alpha, which is outside this thing, right? And then we subtract alpha from our set to consider the set G of omega minus alpha. Then this is some set which is simply connected, but it doesn't actually contain zero. So for example, it might look like this. This could be the set that we have. It could be this spirally thing like this. This could be our simply connected set. Yeah? And as you guys remember from complex analysis, once we have a simply connected set that doesn't contain the origin, then we can actually define a log on this in an analytic way. It'll be smooth, it'll be differentiable everywhere, it'll have all the nice properties. Yeah? Because what's required to define this log is simply to define an angle function that goes around like this in a consistent way. Yeah? Yeah. So this thing is hollow on the entire set omega like this. Yeah. So let's be a bit more specific, i.e. there exists some angle. So I'm going to write the angle function like this from minus alpha into the real numbers, such that Z minus alpha over mod Z minus alpha is equal to, now I just want to define it like this, if I'm running this way, is equal to e to the I theta of Z, like this. Okay? So we can do this, we can have some nice function theta, and the picture I've drawn, theta will take a range longer than not 0 to pi, it could be arbitrary long, we can spiral around as much as we like. Yeah? And how do we define our function like this? We just use this angle function, and log of Z minus alpha is equal to log the base e, which means the real log Z minus alpha, like this, and then plus I of theta of Z, like this, okay? And then this thing is perfectly analytic, everything is good. And it actually has an inverse, right? So whatever the image of our set is under this mapping, it will actually be invertible with the exponential function like this. So if we take e of, go ahead. Sanka, do you have something playing in the background? Just said this very much depends on our domain. So if we have any simply connected domain that doesn't intersect 0, then we can define a logarithmic function, but it absolutely depends on our domain. So this theta depends on our domain, absolutely. Yeah. But for our purposes, it's going to be okay because we're building everything in terms of our domain. We're going to build our function out of all of these pieces. And all we need is that we're building conformal mappings at each stage. You know? So what I'm about to show you is that this thing is conformal, that we can invert it, and the image of this thing is mapping our original set into something that we can go back from with this mapping, or with the inverse of this mapping. Yeah? So let's check that out. So if we take the exponential of g tilde of z, then this thing is defined to be this thing. So this is e of log the base e z minus alpha, like this. plus I theta of z, like this. And what's that? That is just minus alpha, like this, e to the I theta of z. And by definition, that's that thing, so that's just z minus alpha, right? Which is almost what we want. So if we define, do I want to define it? Yeah, I do. Let's define h of z to be equal to e of theta tilde of z plus alpha. Then we have that this guy is exactly going to invert our function, right? So h of, if we define this guy not like this, but like this, of z like this, then what happens then? H of tilde of z is exactly equal to z, right? So h is the inverse, right? H is the inverse. Okay, so the first step is that we've built this mapping that does this thing, right? And now we're going to try and adapt it to get one which will be conformal and do the things that we want. That will map the entire thing into a bounded region inside the unit disk that contains 0. Okay? So the next step is I'm going to show is that G tilde of our set is actually going to miss some point of the complex plane. In other words, the entire image of omega isn't going to be the entire complex plane, and then from that I'm going to adapt it to create something bounded. So next step, we will show actually that there's some disk which is not hit by the image of this mapping G tilde, that there exists some, I don't know what to call it, let's call it alpha, such that alpha and some delta bigger than 0, such that the ball of radius delta around alpha intersect G tilde of omega equals the empty set. Okay, so while I erase the board, tell me why, after we've done something like this, we have the chance to build a conformal mapping that actually makes the image of omega bounded. Think about that and try and give me a suggestion while I erase the board. We show that the image of G tilde of omega is not the entire complex plane. So there exists some alpha belonging to the complex plane, take away G tilde of omega. So we will show. And then later we'll show that we can actually put a disk around it. So why is this the case? Well, to see this, pick an arbitrary W belonging to omega, okay? And then claim, I'm going to take alpha to be f of, or not f, we called it G tilde of W plus 2 pi I. Okay, so why is it the case that this thing will actually not be able to be allowed to be in the image of this thing? So let's draw a picture. If this is omega and this is the image of omega, okay, this is G tilde, and we've picked some particular W, and this is G tilde of W right here. If we take this 2 pi I guy, wherever it is, so I'm going to draw it outside because it actually is outside. So this is G tilde of W plus 2 pi I. What if it wasn't? So after saying that now, I'm going to adapt it and include it. Suppose this wasn't the case. Suppose it actually was inside our set, okay? So suppose we have that this guy alpha did belong to the image of our set G tilde of omega. Well, we know that this mapping e to the z is either plus or minus. I think it was plus, right? It was plus. G of z. This is the inverse mapping. I called it h, right? So h of z, which is equal to e to the z plus. Oh, we've used alpha too many times, right? So let's not call it alpha. Yeah, let's call this beta. Suppose beta belongs to this thing. Then we should be able to invert it with this mapping because it's inside this set that we've shown is already invertible. Yeah? So h of this mapping, G tilde of w plus 2 pi I. By definition, this 2 pi I thing is not going to be noticed when we stick it into this e to the z. Yeah? Yeah? So this will just be the same as h of G tilde of w plus alpha, which is just h of G tilde of w. And therefore, h is not a well-defined one-to-one mapping, right? Because h is the inverse, it's a one-to-one mapping, it's a bijection contradiction. Are you all happy with that step? Yeah? Cool. So it is indeed not inside, it's outside. Okay, so now we're going to show that we can actually put a little disk around this point and still remain outside. So how's that going to work? So suppose, arguing by contradiction, we cannot find a disk. A disk around beta outside. So that means we can get a sequence of points inside the image getting closer and closer to this point. Yeah? So there exists, say, z to k belonging to the image G tilde of omega, such that the limit as k tends to infinity, this guy is a bad guy, like this, right? So then let wk be h of these points. So they're inside this guy, so we can invert them like this. Yeah? And what do we know? Then we know that G tilde of zk tends to this guy here, this guy beta, which is G tilde of w plus 2 pi I. Okay? Just because this is just messing around with the definitions, you know? Cool. So, if this is the case, then let's take the exponential function of everything. Exponential function is continuous, so e to the G tilde of zk is going to tend to e to the GW of w plus 2 pi I, yeah? But that's the same as E of G tilde of W itself, like this. Yeah? Because again, the 2 pi I will just go away. Yeah? And then what happens to this guy? So G tilde was log of Z minus alpha. Just to recall. Yeah. So once we have this, then what is that telling us? That is telling us that zeta k minus alpha is tending to W minus alpha, which implies that zeta k is tending to W. Okay, but WK, these are guys we got from going back from the image, so they are actually inside omega. Yeah, actually inside omega, and so is W inside omega. Yeah, because we just picked a point inside omega, right? So, but WK belongs to omega, W belongs to omega, and on omega our function G is well defined. So, and it's continuous. So we have that the limit as k tends to infinity of G of WK, so G tilde of WK, is equal to G of W, like this, or G tilde of W. But we also have that this is tending towards this thing, which is a totally different number, and therefore it's a contradiction. Yeah? So this contradicts star. Okay, so where were we? We said, suppose we can't find a disk around this point, which was outside. Yeah? That means we could find this sequence of points, zeta k, getting closer and closer from the image G tilde of omega. Yeah? So that's what we express by this. Then we pulled them back with a h, so these were WK here. Yeah? And then this is the guy, so this is the, when I do the relation, yeah, this is the relation we have here. We apply G to both sides, and we get this relation. Yeah? And so this is just expressing that zeta k goes towards this, but now in terms of G of WK. Okay? And then we took the exponential function, which is defined everywhere. It's continuous on both sides, and that actually gave us that WK tends towards W as a consequence. Yeah? But then, by continuity, since WK and W are inside this region where G tilde is well defined, we get that this should be true, but our original assumption was that this was tending to a different number. So it's a kind of a tricky argument. I had to go through this a couple of times to see how this actually was working, but it does actually work. I don't have a good geometrical picture of how this is happening, though. All right, but it's true. It works. So we do have a disk which is strictly outside of the image. Are you all with me here? Yeah? Give me a thumbs up if so. All right, super. So, just as Josh suggested, this now puts us in a good position to actually create something that is bounded by using the fact that we can compose things with a Mobius transform. So, this point beta is strictly outside our set, right? So consider the following mapping. Let's call it G tilde hat, because we still have to do some adaptations. So G tilde of hat of Z. Let's do this. Let's define it as 1 over G tilde Z minus this point beta that we know is definitely outside. Okay? Yeah? Then this thing is definitely a bounded map, because this quantity on the bottom can never get too small, because that's what we just showed. Yeah? So G tilde hat of omega is bounded. And I claim it's also the case that this thing is a conformal mapping. Someone who isn't Josh, tell me why. Why is this a conformal mapping? It's a composition of what? Good. Yeah, so if we let M of z be this mapping 1 over z minus b, then this is a nice Mobius mapping. Yeah? This is a perfectly good Mobius mapping. So then all our mapping G hat tilde of z, it is just M of G hat of z like this. Yeah? So it's the composition of two conformal mappings. It's conformal. All right, so what we've got now is a conformal mapping that takes our arbitrary simply connected set, which obviously can be unbounded, and we now map it to a bounded set. Yeah, that's what we've been able to do with this. I'm going to raise the board, and as I do so, you guys think about how do we go from that to the thing that I actually claimed. Okay, let's draw a picture. So we have our arbitrary domain. So obviously I'm going to draw it bounded, but the point is it doesn't have to be bounded, omega. And we've mapped it into something which is somewhere, so G tilde hat of omega, yeah, which is now a bounded domain. And we have in the statement of the theorem Z0, right? So now Z0 is inside our domain, and it's actually some point inside the image now, like this. This is our point right here, yeah? Yeah? Okay, so what can we do? Let's just define G of z to be eta for some real number eta we'll decide on later. G tilde hat of z minus G tilde hat of this thing. Yeah? Yeah? And what is this? This is just an affine adaptation, right? We're just shifting our thing and then we're rescaling it. Yeah? Yeah? Which is another conformal mapping. So it's like composing on the outside with another conformal mapping. And then this guy does what we want because G of Z0 is equal to Z0 minus G of tilde hat Z0 minus G of tilde hat Z0. It's 0, yeah? So it maps our point onto 0. Yeah? So it's definitely now got 0 inside the image. And in order to make sure it's inside the unit disk, we just need to make eta small enough so that it's contained inside because it's a bounded set. Yeah? Yeah? And make small enough so that G of omega is now contained within the disk, like this. All right, cool. So now what we're going to do is we're going to build a mapping from our arbitrary simply connected set inside the unit disk. We're going to build a mapping from that thing into the unit disk that actually maps completely onto the unit disk. And that is how we're going to be able to create our mapping in the statement. So what have we got? We've got the unit ball like this, or unit disk like this. We have that this is our set inside, potentially, right? This is our G of omega. It's contained inside this. It actually contains the point 0. Oops, point 0 is more in the center, like this. Okay. And we are going to build a mapping from this set here into a unit disk where the image of this thing is the entire unit disk. Okay? That's what we're going to do. Yeah? And it's going to send 0 to 0. And 0 gets sent to 0. Yeah? And if we can do that, then we're in good shape, right? Because then we just take our mapping G, and we take the mapping we just constructed, and we compose on the outside with G, on the inside with this new guy, and that's going to do everything that we want. Yeah? So the first step was just a reduction, right? We're just reducing so that we have this nice bounded set that contains 0 inside the unit disk. Yeah? So then consider this family of functions. So consider a family F of functions. So from now on, I'm going to say omega is this thing, rather, or if you want, I could actually, maybe I'd better to write omega tilde is this thing. It's the thing we've reduced it down to, okay? So consider the family of holomorphic mappings from omega tilde. They're going to map into the unit disk, okay? Obviously, they're holomorphic. We're going to want them to be injective also, so holo and injective. And we want them to preserve 0, so f of 0 equals 0. Actually, let's put it out here. F of 0 is 0. So it's mapping 0 to 0. Yeah? Do we know that this function class is non-empty? Is this function class non-empty? Do we have any examples that we can think of? Can you think of any examples inside this function space? Or this space, inside this set of functions, family of functions? Yeah, it's the identity map. So notice ID belongs to F, so non-empty. All right, so let S be the supremum of F prime of 0 for F belonging to a mapping class like this. Okay, does S have to be finite? Does S have to be finite? Does S have to be finite, people? So I'm going to replace this and call this just omega tilde. So this is our set here. It's a simply connected set. It contains 0. It's open. Yeah, and we're talking about all families that are holomorphic mapping into the unit disk. Yeah. And we're considering this. Does F prime have to be, does S have to be finite? Come on. The answer is yes, but why? So this is think about the principle that we talked about already a little bit, and it's going to keep coming up. That holomorphic mappings are very strong because we can control higher order things in terms of the function itself, right? So this thing is putting constraints on the function itself, yeah? And this has something to do with the derivative, but we can control the derivatives, the higher derivatives, the winding number, all kinds of things just from the function, right? Yeah? And how do we control the derivative from the function? What's the tool? Gaussian integral formulas. So go ahead, Sanka. Why is S bounded then? Here's a hint. such that it's contained within our set like this. Yeah. No. The maximum modulus principle would tell us that the absolute value of the function is achieved on the boundary. That's not going to help us here, right? Because a priori I don't see how that's going to help us. So we can just take absolute values around everything, right? Yeah, because this thing on the bottom, there should be 0 right here. I'm doing this at 0, like this. Yeah, this thing at the bottom is always going to be bounded above by r squared. Yeah, and the thing on the top, the function is mapping into the unit disk, so that's always bounded above by 1. Yeah. So what does this give us? This gives us, this is less than 1 over 2 pi, like this, the supremum of f over r squared on this boundary, like this, yeah? And that is less than 1 over 2 pi r squared because this function is bounded. Everybody happy? Yeah? So this is a universal bound. It doesn't depend on f because f is this family into this thing. Yeah? So this is a finite thing. This is a finite number. Yeah? Cool. All right. So our claim is that we can actually find something that actually achieves this. So claim. There exists some f tilde belonging to our function class f. Actually, I'm just going to call it f because we're going to need it later and it's going to come up so much. F such that f prime of 0, absolute value, is this maximum here. Yeah? All right, so how are we going to do this? Give me suggestions. Someone hasn't spoken yet. So the natural thing is to try and get there from the limit, yeah? So by definition, so for each k, there exists some fk belonging to this function class such that f prime of fk of 0 is bigger than s minus 2 to the minus k. Yeah, for sure, by definition. Yeah. And the natural thing would be to obtain our f as the limit of these guys. Yeah. Do we have any hope to do that? So, want to define f as a limit of a subsequence. But why can we do it? Do we have any kind of limit of a subsequence to begin with? First, let's talk about if we have any kind of limit of any subsequence, and then let's see if it's in the space. Indeed, why is it normal? Why is it normal? Don't look in your notes, just think about it. What was the one hypothesis we needed on our family of holomorphic functions to make sure that they were normal? How did equibounded? Is this an equibounded family? Yeah. They're very much equibounded, right? They're all mapping into the unit disk, so the absolute value is always less than 1. So it's an equibounded family. Yeah. So this is a normal family. So we can extract a subsequence that converges. So since F is a normal family, so I'm going to not relabel the subsequence. This is something that you'll see going forward a lot. You end up taking sequences and subsequences, and it gets too many notations. So you'll often just write the subsequence as the sequence. So there exists subsequence not relabeled. And then let's spell that word. Such that the limit, or let me write this in words, such that Fk tends to F on compact subsets of omega. This is uniform convergence. Write that as well. Uniformly on compact subsets. Okay. All right, cool. So there is some f as a limit. Is this function f going to be inside our function class? So what does it need to be? So it needs to be holomorphic, injective, and f of 0 has to be 0. Can we satisfy that? Is the limit going to be holomorphic for one thing? Yeah, it's holomorphic. Yeah. Okay. Is f of 0 going to be 0? Yeah. Why so? And we have convergence on compact subsets, so like this, yeah? So this is true. Okay, is it going to be injective? Yep. Yep. And F is injective by previous theorem. It could also be constant. Or constant. That's true. It could also be constant. But if it was constant, then it wouldn't be injective. Wait. It's either injective or it's constant, right? So why can it not be constant? Well, if it was constant, then the derivative would be 0, right? We've taken S to be the supremum of all these guys. And there is at least one guy in this family, yeah? And since, oh, good question, I didn't think about that. So since the identity belongs to F, we know that at least S is bigger than or equal to 1. And so this limiting function like this equals S, which is bigger than 0, so non-constant. But I've used something here when I've concluded this. What have I used when I conclude this? Why am I allowed to say that? Yeah, well, that's how we chose the sequence, but why do I have the right to claim that the limit satisfies this? That's true. That's true, and that was part of the theorem we proved about if we have a family of holomorphic functions that are bounded, and not only that the functions converge on some subsequence for some subsequence. So given a sequence of that family, a subsequence converges, for the functions, but also a subsequence will converge for the derivative. Yeah, remember this? Because the same argument applied that Cauchy integral formula allowed us to control the derivative of the derivative, and show as equicontinuous or compact set. So in this subsequence that we chose that converges, we can also assume that the subsequence was chosen so that the derivatives converge to the derivative on compact set, and therefore this thing, the absolute value is continuous, is the limit as k tends to infinity of the subsequence, and therefore, because we've chosen it getting up to S, it's actually equal to S. Cool. All right, so what we'll do next time is the final step of the proof, which is to show that after we've got this mapping S, now that we have this mapping S, the only way it can have this property of maximizing this derivative is if it's sending the entire image covering the entire unit disk, filling up the entire unit disk, okay? Which is kind of a tricky and surprising argument. But once we've got that, then that completes the proof. Cool. All right, that's it for today. Any final questions before we say goodbye? Everybody good? All right, see you on Friday and we'll finish this proof. Have a great day. Bye-bye, people.